In this lecture, we are going to look at how to do some basic computation in order to create a risk-return plot and work with portfolios and code. For this lecture, we'll be focusing on synthetic data just to get a hang of what's going on. Then, in the next lecture, we'll get back to working with real stocks. This lecture is going to walk you through a prepared Colab notebook, although a very good exercise, which I always recommend, is once you know how this is done, to try and recreate it yourself with as few references as possible. As always, you can check the lectures, how to code by yourself, and how to practice for a more in-depth discussion. If there's anything in this lecture you didn't understand, or you think I missed a step, or didn't explain why we were doing something, please use the Q&A to inquire. As usual, you can look at the title of the notebook to determine what notebook we are currently looking at. So let's start by importing pandas, numpy, and matplotlib. Next, I'm going to set a random seed for numpy. Usually I don't do this because usually I work with code that generally works the same no matter what random numbers you get. And I like my students to be able to see that variability and not be shocked by it. But for this example, there will be some code where if we don't set the random seed, there's a chance that your data will look very different from mine, which is not good. So setting a random seed will ensure that your results look like what you would typically expect. Okay, so next, we're going to create some parameters for a synthetic two-stock portfolio. We'll start by generating the expected returns. We'll draw these from a normal distribution with mean 0 and standard deviation 0.01. Next, we'll generate some random correlation between the two stocks. We'll draw these from a normal distribution with mean 0 and standard deviation 0.01 as well. Next, we'll generate the standard deviation for the two stocks. Since standard deviations must be positive, I've sampled 2 points from the standard normal and then put them through an exponential. So this will ensure that both sigmas are positive. Next, we're going to create the covariance matrix. We'll start by creating the diagonal elements, which can be accomplished by calling the diag function on sigma squared. As you can see, we get the squared sigmas on the diagonal and 0 on the off diagonals. Next, we need to fill in the off diagonals, since we have a non-zero correlation between our two assets. We'll call the covariance sigma 1, 2, which is equal to sigma 1 times sigma 2 times rho. Note that, since the covariance matrix is symmetric, this same value can be assigned to cov 0, 1 and cov 1, 0. Alright, so next, as you know, the weights of a portfolio must sum to 1. One way to generate random weights that sum to 1 is to generate any set of random numbers and put them through the softmax. The softmax function exponentiates each element, which makes them all positive, and then divides by the sum of the exponential elements. So everything that comes out of the softmax will be positive and sum to 1. This is one way to generate random portfolio weights, but we'll see others as well. Okay, so next, we're going to generate a bunch of random portfolios, calculate their expected return and risk, and then plot them in the next block. So let's start by setting n equals 1,000 portfolios. Next, let's create empty arrays to store our returns and our risks. Next, we enter a loop that goes for n steps. Inside the loop, we generate two numbers from the standard normal, and then pass them into the softmax. This gives us w, which is properly normalized to sum to 1. Next, we calculate the expected return. This is the mean return for each asset, dotted with w. Next, we calculate the risk. This is the square root of the variance. The variance is w multiplied by the covariance multiplied by w again. Note that in NumPy, we work with one-dimensional arrays when we want to represent vectors, so there's no need to transpose them as we do in the math. Finally, we save the expected return and the corresponding risk into our arrays for the returns and the risks. Alright, so next, we're going to draw a scatter plot of our randomly generated portfolios with the risks on the x-axis and the returns on the y-axis. We'll set the transparency to 0.1 so we can see all the points. Okay, so as you can see, we get a plot that curves downward. Now you might ask, why isn't this a nice hyperbola? Well, let's go back up and look at what the returns actually are. So we see that the return of the first asset is about negative 0.008. The return for the second asset is about positive 0.002. Notice how the return of the first asset is much larger than the second. Therefore, we can expect that most positively weighted portfolios with these two assets will have negative return. Okay, so let's scroll back down to our plot. As a side note, notice how the extreme ends of this plot are pretty light in terms of the dots. This is because the softmax function tends to avoid very extreme values. Therefore, the softmax function can never give you a value of 0 or 1, which we know is actually possible. Also recognize what the limits of this curve are. At the top end, we have the return for the second asset, about 0.002. At the bottom end, we have the return for the first asset, about negative 0.008. Therefore, these correspond to when we are only invested in either the first or second asset. Every point in between is a portfolio where we have a combination of the two assets. So in the next block, we're going to use a different way of generating our weights. This loop is almost the same as before, except for the part where we generate the weights. So to generate the weights, I'm going to create a single random number between 0 and 1. We'll call this x. Then I'm going to set w to just be a 2-element array containing x and 1 minus x. Okay, so let's run this. And let's draw our plot. Okay, so you can see that with this risk-return plot, the ends are a bit darker because the random function doesn't have any aversion to values extremely close to 0 or extremely close to 1. Technically, it should be uniform. Again, notice how most of the portfolio returns are negative. Okay, so in the next block, we're going to do the same simulation, but this time, we're going to allow short selling. That is to say, our weights can now be negative. To do this, when I generate x, I'm going to subtract 0.5. That means that x will always be between minus 0.5 and plus 0.5. W can still be an array containing x and 1 minus x, since the constraint that the weights must sum to 1 still holds. So let's run this. And let's plot the result. Okay, so we can see that now we get this nice full curve with both positive and negative returns. Why is this? This is because we are now allowed to short sell on the asset with negative returns, which gives us positive returns on our portfolio. So when you short sell on an asset that drops in price, you make a profit. By the way, note that our weights are not symmetric. Since x is between minus 0.5 and plus 0.5, what is 1 minus x? 1 minus 0.5 is just 0.5, so that's the minimum value we can get. But 1 minus minus 0.5 is 1.5. Therefore, this value varies between 0.5 and 1.5, unlike the first weight, which varies between minus 0.5 and plus 0.5. If you want it to be more balanced, you could shuffle the weights to get a wider range. By doing so, the range of possible values would be minus 0.5 to plus 0.5. Alright, so next, we're going to look at a 3-asset portfolio, and you'll get to see how this plot changes. So first, we're going to go through all the same steps to generate our mean and covariance. We'll start by generating the means from the normal, again with standard deviation 0.01. Next, we generate sigmas by exponentiating samples from the standard normal. Next, we generate our rows by drawing from the normal with mean 0 and standard deviation 0.01. Notice we have 3 values. This is because we have the correlation between asset 0 and asset 1, asset 0 and asset 2, and asset 1 and asset 2. Next, we combine the sigmas and the rows to generate the covariance. You might want to look at your notes to verify that what I've done is correct. Okay, so next, we're going to generate our random portfolios. Again, we have a loop that goes for 1,000 steps. The main difference, of course, is in how we generate the weights. In order to generate the weights, I've first sampled 2 points from the uniform distribution between minus 0.5 and plus 0.5. We'll call these x1 and x2. Next, I create the weight vector w with elements x1, x2, and 1 minus x1 minus x2. Note that this sums to 1. Let's consider the range of values for the third value. If x1 and x2 are both 0.5, then we get 1 minus 1, which is 0. If x1 and x2 are both minus 0.5, we get 1 plus 1, which is 2. So again, these weights are imbalanced, and a simple way to balance them would be to shuffle the order. Note that there are many ways to generate random weights, so you are encouraged to try different things. Alright, so let's run this. And let's make our plot. Alright, so what do we see? We see that this no longer forms a nice, well-defined curve. Instead, we can see that points can now appear inside the curve. This is a consequence of having more than 2 assets. There is now no formula that connects the portfolio variance to the portfolio return. As a final note for this lecture, I want to note that there is a lot more stuff in this notebook that we are not going to go over in the lectures. This is because we're going to go over them when we're looking at actual stocks, and I didn't see a real point in doing them twice for every topic in this section. However, it's always nice to be able to use your algorithms on both synthetic data and real data, and just doing the same exercise more than once will give you more familiarity with the material. So if you like, check out the rest of this notebook for examples on how to implement some of the other ideas we discuss later in this section.